بسم الله الرحمن الرحيم. نبدأ اليوم محاضرة الثانية من سلسلة محاضرات Digital Signal Processing. عنوان topic أو المحاضرة اليوم راح يكون Discrete Time Signals. Discrete Time Signals. احنا في المحاضرة السابقة تكلمنا عن السيجنالز in general، واليوم راح نتكلم specifically عن discrete time signals. وعادة في كثير من الأحيان نختصرها نقول إنه DT signals. DT discrete time. Okay. The discrete time signals إلها عدة sources. السورسز يعني أهم two sources للدiscrete time signals اللي هم إنه بيكون عن طريق السامبلينج. So sources of discrete time signals are first one by sampling of continuous signals, or the signal is really or inherently discrete in nature. Inherent discrete time signals in nature. اوكي، يعني اكزامبل زي هذا على النوع الاول راح نشوفه كمان شوي، لكن اكزامبل على النوع الثاني يعني ممكن تكون عباره عن signals coming from sources like sensors or transducers, or coming from space aircraft going to ground and sending signals to earth. هذه بتكون في معظم الأحيان discrete time signals. So it's like taking the readings of transducers or sensors every some specific period of time. Okay, this is the second type. Okay, going to the first type, which is more important for us right now because we need to see what will happen if we sample a continuous signal. Then afterwards, both of them will be dealt in the same fashion. يعني راح نتعامل مع الاثنين في نفس الطريقة، لكن خلينا نتفرج على السامبلينج أول إشي ونشوف كيف راح نعمل سامبلينج وشو بصير في السيجنال when we do sampling. Okay, when we talk about sampling now, we are talking about an ideal sampler that has discrete time specific or discrete time periods، لكن السيجنال راح تكون أو الامplitude of the signal will be continuous. Okay, let me take this here as an example. Let me take variation of a signal and look at it together with you. Okay, I'm gonna sample a signal, take my zero. So my zero instant here, this is the sample at 0, this is the sample at 1, the sample at 0. So this is actually sampling, and those stems اللي عبارة عن الأروز with the circle on top هذول بنسميهم stems. احنا هذول الstems هم اللي بيمثلوا الديسكريت تايم سيجنال اللي راح تكون موجودة عندنا. ف this is in the negative time So this is 0 minus t, minus 2t, minus 3t, minus 4t, minus 5t, and so on. And here we have 0, 1, 1t, 2t, 3t, 4t, etc. So this is how we do sampling actually. And this is a graphical representation of sampling. We know for sure that this signal here, or the amplitude here, is x. If we call this continuous signal xa of t, and a here means analog, signal. So xa of t is an analog signal, continuous signal in time. We do the sampling, we take those stems to be our discrete time signal. So the value at minus 2t, this is xa at minus 2t, and we will call it as x of 2t. And then afterwards, we will skip this t and we call this as x of 2. Sorry, minus 2. Minus 2. Okay, so we have x at minus 2. X at minus 2 means this is x at minus 2 times the sampling period. T is here defined as the sampling period. So xa of t, when we take xa of t at t equals n times t, so we will get xa of nt, which we will call it x of n. So notice that the regular brackets here, now we have square brackets here to show that we are dealing with discrete time signal, not continuous time signal anymore. So x is the variable, n is the independent variable, x is the amplitude, n is the independent variable, and the square brackets means that you are dealing with discrete signal. This is a discrete signal. Okay. This discrete signal has also another name. We call it also sequence. So we call this one is also a sequence. X of n is a discrete signal. Another name, for simplicity, we call it a sequence. Okay, where here t is the sampling period, so t is the sampling period, and ft is equal to 1 over t is the sampling frequency. So t is the sampling period. وحدة التي أو اليونت للت هي seconds. f sub t is 1 over t is the sampling frequency in hertz or in samples per second. Number of samples per second. So if you say that you have a sampling frequency of 1 kilohertz, 1000 hertz, means that you are having 1000 samples in 1 complete second. So this is what we mean by the sampling frequency. Okay. Notice here that the amplitudes here that we have here are the values of the continuous function at that particular point, as we mentioned here in x of a and t. So if those values, let's say that this is an amplitude of 1, 2, 3, 4, 4.5, 5, 4.5 again, and this one is 0, minus 1, minus 2, minus 3, minus 2, minus 1, and so on, we can say that okay, let me move here, and we can represent the sequence or the discrete time signal using the sequence representation, which will be as follows. So we can say that, okay, x of n is equal to, let's put those 3 dots, means that the sequence or the signal is infinite from the left side, from the negative side. And if we have another 3 dots, it will be also infinite from the positive side. So let's take for representation, starting from minus 2t. So you have 4, which is this one, comma, 3, which is the next, comma, 2, 1, 0, minus 1, minus 2, minus 3, and another 3 dots to represent the signal. So x of n, the discrete time signal that we have here, is represented by those 2 curly brackets. 3 dots means that you have an infinite sequence from the left side and also infinite from the right side. And we have those values. Now, there is one missing point here, which means that, okay, you put the points in a sequence, which means that everyone is followed by the next one, but the one with n equals 0 is not shown here. I mean, you don't know which one will be for the index equals 0, so we have to put another information. For n equals 0, we have a value of 2, which is here, so we have to put an arrow downwards. So this arrow means that this one is for n equals 0, and what we have to the left is the negative side of the indices. So for n, this one is for n equals minus 1, n equals minus 2, and so on. And for the right-hand side, this is for n equals 1, n equals 2, and so on. Okay? So you don't have to have all those, only an arrow showing that this is the index n equals 0. What we have to the left is the left-hand side. To the left-hand side are negative indices, and here are the positive indices. So those are the values. So this is x of 0, this is x of minus 1, x of minus 2, and so on. And here we have x of 1, x of 2, x of 3. Okay. Please notice that the indices here does not mean an absolute value 1. It means that you have, when you have n equals 1, it means that you have one time period or one sampling period. If you have n equals 2, you have 2 sampling periods. If you have n equals 10, then you have 10 sampling periods. And what I mean here is, let's say x of 10. What does that mean? It means that you have x of 10t, where t is the sampling period. So if the sampling period, let's say, is equal, for example, if the sampling period is equal to 0.1 second, this means that this one is equal to x of 10t, means that this is x of 10 times 0.1, which is equal to x of 1 second. So in actual or in real life, this means that this x is the amplitude of x of t when t is equal to 1 second. Okay? So this is the case. Okay, so enough for introducing the the discrete time signals and the sequences. Okay, I will leave this one here and go to the other side. Okay, so this representation here is called the sequence representation. The sequence representation of DT signals. There are also other representations. So this is the first one. The second one is the pictorial representation. Pictorial means that you draw the function. Let's take the function as an example. If we take this one here, this is a representation of some x of n. Pictorially means that you draw it graphically, let's say. So this is let's say 1/2, 1/4, 1/8, 1/16, 1/32, and so on. And here it is equal to 0 in the other side. So this is 0, 1, 2, 3, 4, and 5, etc. This is n, and this is -1, -2, -3, etc. So this is a pictorial representation of x of n, which is exponentially damping function. Okay, third representation for this signal we could use the tabular method. And the tabular method means that you have a table. This is n and x of n. And we can say that for -2, -1, 0, 1, 2, 3, 4, etc., x of n. So we have here zeros. At 0 we have 1. At 1 we have 1/2. At 2 we have 1/4, 1/8, 1/16, etc. So this is the tabular method of representing a sequence. We have also another form to represent a sequence using the functional method. Functional representation. So we have the functional representation, and we can represent x of n as 1/2 to the power n for n greater than or equal 0, and 0 for n less than 0. Okay? Notice here that we used here for n greater than or equal 0, so 0 is included here. When you say that n is less than 0, all the values that we are using here are integer values. So x of n is not defined for non-integer values. So when you say n less than 0, the first integer coming below 0 is -1. So this one will be defined from -1 and below for integer values. And this one is from 0 and above for integer values. Okay, so this one, and this one are three different values or three different representations for the same function, x of n, which is to 1/2 of to the power n for n greater than or equal 0 and 0 otherwise. Okay? All right. Okay, so let's go a little bit further with discrete time signals and define some parameters needed. Okay? Let's define the length. The length of discrete time signals. Okay, we have Based on length of discrete time signals, we have two types of signals. It's either finite length sequences or discrete time signals, or infinite length sequences. So we'll start with the finite, number one, finite length sequences. A finite length sequence is defined for finite period of time. Which means that n is defined between n1 and n2, where n1 is greater than minus infinity and n2 is less than infinity. So you have a finite value from the left side and another finite value from the right side. Okay? And also, n1 is less than or equal n2. Of course, you can say n1 equals n2. If you have n1 equals n2, then you have only one single point in the sequence. Okay, if n1 equals to n2. So the length or duration of the sequence is n equals to n2 minus n1 plus 1. So this is the length of the sequence. The number of values in the sequence is defined in this manner. Okay? So if you say, okay, we'll take an example in a while. Just a second. Let me just move here also, once again, and continue. Okay. A finite length sequence can be considered infinite by padding or appending zeros. So even if you have a finite duration, you can add zeros from the left side, zeros from the right side, and get an infinite sequence, although it has zeros from both sides, but it's infinite. So finite length sequence can be also considered as infinite length sequence by padding zeros from both sides, left and right. Okay. Also, a length n sequence. And this is like a definition. Length n sequence is often referred to as n-point sequence. So if you have, let's say, n-point sequence, 8-point sequence, we say a length 8 sequence. So this is like a definition that we introduce the sequence in this manner. For example, if x of n equals to n squared minus 1 for n between -2 and 3. So x of n is of length 6. From -2 up to 3, so you have a length x sequence, length 6 sequence, sorry, and x of n can be evaluated like this. X of n starting from -2, if you apply it here, it's 4, -1, it's 3. If you apply -1, so you have 0. If you apply a 0, then you have -1, and we have then the arrow here. And if you have 1, then you have a 0. And if you have 2, you have 3. And if you have 3, then you have 9 minus 1, it's equal to 8. So this is a finite length sequence. The length of the sequence is 6, starting from -2, 0, sorry, -2, -1, 0, 1, 2, 3, the indices. So this is my, for n equals 0. Go to the left, this is -1, -2. Go to the right, 0, 1, 2, and 3. Okay, so this is the sequence. And you can check it out that this is N2, and this one is N1. The length of the sequence N is equal to N2, which is 3, minus -2, which is N1, and plus 1. So this is 3 plus 2 plus 1 is equal 6. 6 samples. So you have 6 samples in the sequence. Okay? So this is the first type of the sequences based on the length of the sequence. So finite length, we have some good information about it. Let's go to the infinite length sequence. So the second type is the infinite length sequence. The first type of infinite length sequence is the two-sided sequence. So it's infinite from the right side and from the left side. It's defined, this one is defined for all n. Okay? So the sequence is defined for all n. You have values all over. So you have values from the left side going to infinity, from the right side going to infinity. So my n1 is minus infinity and n2 is plus infinity. So this is the two-sided sequence. Okay. The second type is right-sided sequence. So we have a right-sided sequence, and here the sequence is defined for n greater than or equal to n1. So the sequence is defined for n greater than or equal greater than or equal n1, and it looks like this. So you have at n1, and starting from n1 and above, you have values, and here you have below n1 are all zeros. So below n1, all values are 0. So this signal goes to the right. To the left, it's all zeros, starting from n1. Now, there is a special case here. If n1 is greater than or equal 0, then we call this sequence as causal sequence. Causal sequence. Okay? This name, please keep it in mind. We'll discuss it later. Okay? So if n1, if this n1 is not negative, if it is greater than or equal to 0, n1, if it's greater than or equal 0, we call this sequence a causal sequence. Okay? If not, then it's not causal or anti-causal. Okay. The last category, or the last type of infinite sequences, which is part C, is the left-sided. The left-sided sequence. The left-sided sequence, and here the sequence is defined for n less than or equal n2. So if we have a sequence, then we have, this is n2, sequence continues to the left, going from n2 and above n2, all the values are zeros. So the values here are zeros, the values here are non-zero values, and starting from n2 and going below to the left, this is why we call it a left-sided sequence. The sequence continues to the left until minus infinity. Here, the right-sided sequence, the sequence continues to the right up to n goes to infinity. And one last comment here, if n2 is less than 0, then we call the signal anti-causal. So if this one is greater than or equal 0, we call it causal. If n2 is less than 0, we say it's anti-causal or non-causal. Okay, non-causal. Okay. So this is about the length of the sequence. Let me go to one last point here, talking about the general amplitude of the sequence, not the duration, talking about the amplitude. And we will define something called the complex sequences. Complex sequences. So in complex sequences, we know that you have a real part and imaginary part in complex numbers. Here, we also have a real part of the sequence and an imaginary part of the sequence. So there are two types of representation for the complex sequences. The first one is the rectangular form. The rectangular form. And here we can say that x of n is made of two parts, x real of n plus j times x imaginary of n. So you have a real part of the sequence, and you have an imaginary part of the sequence multiplied by j, and we all know that j is equal to the square root of -1. Sometimes we call it I. Okay, but in electrical engineering we call it J because I is mostly reserved for current. I represented the current in electrical engineering. Mathematicians usually or physicians, physics people, they use I. Okay, the second representation is the polar form. The polar form representation, and here x of n is represented as magnitude of x of n with a phase e to the j theta of n, where magnitude of x of n is equal to the square root of x real of n squared plus x imaginary of n squared under the square root. Okay, so this is the magnitude. And the phase theta of n is the phase, which is equal to tan inverse of the imaginary part divided by the real part. Tan inverse of those values. Okay? So those are two representations of the complex sequences. And the last point here is defining the complex conjugate of a sequence, of a complex sequence. The complex conjugate of a complex sequence. The complex conjugate of x of n is defined as x with a subscript of star equals to, the real part is the same, but the imaginary part has an opposite sign. So we have an opposite sign for the imaginary part. This one here. So we have a minus sign. And if we use the polar form, it's also, the magnitude is the same. So the magnitude is the same, but the phase angle will be with a minus sign. So this is the complex conjugate of a complex sequence. In the rectangular form, we have an opposite sign for the imaginary part. In the polar form, we have a minus sign in the phase. So this one here is the phase angle. So this one is the phase angle, okay? With this, we come to conclusion to our class today, to our lecture. Thank you very much, and I hope you will enjoy it. Bye-bye.